Hello, thank you for joining us today. My name is Sarah Brady. I'm the Deputy Director of the California Council on Science and Technology. I'd like to open our briefing today by acknowledging that I am presenting to you from the tribal land of the Nisenan people. Sacramento has been a gathering place for many local tribes. We acknowledge the Southern Maidu people to the north, the Valley and Plains Miwok people to the south of the American River, and we would also like to honor the Patwin Wintun people to the west of the Sacramento River. Today, I'll introduce CCST, our Disaster Resilience Initiative, and then welcome Katerina Robinson here on behalf of Senator Nancy Skinner, our partner for this briefing. The California Council on Science and Technology is a nonpartisan, nonprofit organization established over 30 years ago at the request of the legislature. CCST was created to provide science and technology advice from the wealth of outstanding academic and research institutions in our state directly to policymakers. California is lucky to have such an incredible network of expertise, and our job at CCST is to help amplify and translate the expertise in this network into actionable advice for policymakers. We do this through a number of mechanisms, including briefings like the one you are attending today. We host workshops, write peer-reviewed reports, and run the CCST Science Fellows Program, where we place PhD scientists and engineers in the executive branch and the legislature for a year of government service and leadership training. As part of our mission, CCST is advancing work related to our Disaster Resilience Initiative to help the state better prepare for and respond to ongoing, complex, and intersecting disasters that affect public health, our economy, and our environment. These include climate change, extreme heat, power outages, and the COVID-19 pandemic, which are radically disrupting the ways in which Californians live and work. These disruptions, while often destructive and painful, can provide us opportunities to redesign our systems to be more resilient and sustainable. Through our Disaster Resilience Initiative, we seek to deliver science and technology advice to reduce harm and improve the lives of all Californians. Today, we are focusing on how clean hydrogen technology can help us decarbonize California, increase grid reliability, and improve air quality for communities across the state. Today's briefing is in partnership with Senator Nancy Skinner, who has long worked to address California's climate change needs and innovate on how we integrate clean energy into our portfolio. I'm pleased to introduce her Capital Director, Katerina Robinson. Katerina has deep expertise and experience in energy and environmental policies. I'm excited to hear more about Senate Bill 1075. Welcome, Katerina.
Thank you, Sarah, and thank you to CCST for this briefing. I'm filling in on behalf of Senator Skinner today, who is presenting bills on the floor all week this week for House of Origin deadlines. So I'm here to speak in her place. We're living in a time of great innovation in the energy sector. It's an exciting time. Our society is setting new goals for itself. We're restructuring the way we produce and consume energy. And that presents all sorts of new challenges for the grid, for our pipeline system, for our end uses for this energy and for these fuels. We have different types of resources. We're trying to use renewable resources only, and they behave differently on the grid. They produce at different times. They are in different locations than traditional fuel sources have been, and they are requiring technological upgrades and, in many cases, job transitions. And all of this we are doing at the same time that we are trying to balance the cost of electricity and energy to our ratepayers, keeping communities safe, and also providing certainty that we will have energy when we need it, when our consumers are turning on the lights, when our constituents are turning on the lights. Hydrogen, and specifically green hydrogen, is one of the answers. It's not the only answer, but it's a really exciting answer to a lot of these energy and fuel issues, because it offers so many different solutions for so many different problems. It is a real switch hitter or utility player since it's baseball season, and it significantly reduces air pollution from a lot of end uses that today use diesel or other very dirty fuels. So it's something that the legislature has been looking at more and more, and our state agencies have been looking at more and more as a tool in our toolbox as we work to decarbonize our system. Some of our presenters today will talk about how hydrogen can be made from clean electricity and clean resources. So I'm not going to go too far into that, but it can also decarbonize really difficult to decarbonize sectors that we don't have a lot of other answers for, like shipping and air travel. And it helps us preserve well-paid jobs as we do this transition into new types of energy. There's been a lot of very exciting development in all over the world and in California and the United States on hydrogen recently. Spain earlier this year announced in their High Deal España that they are planning to install 9.5 gigawatts of solar power and 7.5 gigawatts of green hydrogen electrolyzers that are making hydrogen from that solar power by 2030. So these are real commitments that are happening by countries to move toward green hydrogen. Australia, that's long been a driver of green hydrogen policy in the world, has announced the first of 3 large hydrogen infrastructure projects in Queensland and have started with a $2 billion investment into that project, which is supposed to produce 65 tons of green hydrogen per day. And then right here in our backyards, many of you probably saw that in Los Angeles, SoCalGas has announced their Angeles Link, which is an intention to create a fully green hydrogen pipeline that serves the LA basin and would displace 3 million gallons of diesel fuel per day if they build it out as they expect. And that's about 3.1 million cars off the road if all of that is used to displace gasoline or diesel. And in San Francisco, Hornblower just won a federal grant to create a green hydrogen bunker fueling station for ferries and boats in San Francisco. So although a lot of this seems theoretical to us policymakers, it's really happening on the ground. It's happening now. And Senator Skinner is working on a bill, SB 1075 in the legislature, which this year helps to make California competitive to receive some of the federal funding that's coming out for hydrogen. The federal government has last year announced money for hydrogen hubs throughout the United States, and one specifically for clean energy. California would like to be competitive to get that here in our backyard. And it also includes some additional language that would require the Energy Commission to provide some more details about how hydrogen needs to be generated in California in order to be able to make renewable electricity from that hydrogen, and asks other state agencies to continue to include green hydrogen in their decarbonization strategies. And with that, I'm very excited to hear from some of the presenters today about what's going on in hydrogen and get into some of the technical details about, what barriers do we still face to produce green hydrogen at a scale that will truly be cost effective for use in California and throughout the United States. And thank you again, CCST, for hosting this. I'll kick it back to Sarah.
Thank you, Katerina. We're lucky to have your expertise here in the legislature. While CCST as a nonpartisan organization doesn't support or oppose specific pieces of legislation, we love to dig into the science behind policy ideas. So we're very happy to have heard from you on SB 1075. Next, I would like to introduce our moderator, Dr. Naomi Bones, co-managing director of Stanford's Hydrogen Initiative and managing director of the Natural Gas Initiative. Naomi is an experienced practitioner in the energy sector with expertise in reservoir geophysics, investment analysis, and strategic planning. Her primary focus is on developing technology solutions related to hydrogen, natural gas, and decarbonization. Naomi.
Thank you so much, Sarah. It's a pleasure to be here today with all of you. While California has made significant strides in reducing its greenhouse gas emissions, there are many challenges that we have to overcome in order to achieve carbon neutrality by 2045. Hydrogen could be key to decarbonizing some of the hard-to-abate sectors like cement and steel production, agriculture, and heavy-duty transportation, as well as ensuring energy reliability in a grid that is increasingly powered by intermittent renewable resources like wind and solar. So I'm thrilled today to have 4 experts with me who work on different facets of hydrogen research to discuss the opportunities to use hydrogen to decarbonize California and some of the technical challenges that we are working on to make this a reality. I will take a moment here to introduce each panelist and ask them to provide a brief introduction of their expertise and discuss a specific challenge that they're working to address with regard to hydrogen for decarbonization. Our first panelist is Dr. Luca Mastropasqua, who is a research scientist at the National Fuel Cell Research Center at UC Irvine. Luca.
Thank you, Naomi. Yes, I'm a senior scientist at National Fuel Cell Research Center at UC Irvine. I'm working on electrolysis systems for hydrogen production and all renewable fuel production that could use renewable sources of electricity, wind and solar specifically, to produce renewable energy carriers that can be used for decarbonizing some of the sectors that has been mentioned already. One of the sectors that I'm focusing on at the moment is steel. So we currently work on using high temperature electrolyzers that can be integrated or more easily integrated into heavy duty, let's say hard-to-abate stationary sectors such as steel. And hydrogen is really one of the few solutions that we have to decarbonize steel production, where the feedstock of these processes needs to become renewable. So electrification is not the only solution for these sectors.
Wonderful, thank you, Luca. Our next panelist is Dr. Arun Raju, who is the Associate Director of Operations at the Center for Environmental Research and Technology at UC Riverside. Arun?
Thank you, Naomi, and hello, everyone. As Associate Director at UC Riverside's Center for Environmental Research and Technology, CE-CERT for short, I'm involved in long-term initiatives, including initiatives on hydrogen production and deployment and how to help accelerate that. I'm also a research faculty here with heavy emphasis on renewable fuels, particularly hydrogen. And I work on the effect of hydrogen on materials as we start deploying hydrogen to understand how hydrogen can degrade or embrittle some of the metals commonly used in systems, hydrogen use in the transportation sector, and also hydrogen production from renewable resources, especially biomass and waste. That's kind of my background. In terms of a particular sector to decarbonize using hydrogen, I just want to take a step back and kind of provide a little bit of context. You know, when we are talking about decarbonizing using hydrogen, it's also important to look at the criteria pollutant and toxic emissions that come from several of these sectors. So when we look at ways to mitigate both of these emissions, hydrogen turns out to be the most viable choice technologically and resource-wise for many of these sectors. So these include, I think, heavy-duty industry and some of the other sectors Naomi mentioned. I'm going to particularly say that heavy-duty transportation offers a very important opportunity to be able to use hydrogen to decarbonize significantly, but also address the air quality issues, especially in communities that experience a disproportionate burden, where I'm based in the South Coast region of California. So for heavy-duty transportation, the technology is pretty much there, heavy-duty fuel cell trucks. And it's, I think, primarily a question of building the infrastructure and accelerating deployment and continuing to work to improve technological efficiencies. And it can make quite a bit of a dent in reducing California's greenhouse gas emissions, but also the criteria pollutant toxic emissions.
Thank you, Arun. Our next panelist is Dr. Lou Fulton, who's the director of the Sustainable Transportation Energy Pathways Program at the Institute of Transportation Studies at UC Davis. Lou?
Thank you. Thanks, Naomi. Yeah, and I also am a little separate from the role with the STEPS research cluster that I lead. We have a large hydrogen project, I call it large for us anyway, ongoing, where we're looking at a systems analysis of hydrogen in California on a spatial basis. So we're looking at possible demand nodes, everything from refueling stations to heavy industry, and where they are, what they could demand in the future, where the hydrogen could come from, especially green hydrogen, and how you would set up a transmission system to get the hydrogen from supply to demand. So we have this big modeling project ongoing, and we have a new, our first working paper on that we've now released for review. So I'm happy to share that with anyone. As far as the, what should we be trying to decarbonize with hydrogen question on the end use side, I'm going to mention light duty vehicles, cars and household vehicles, because it's so easy to just overlook it. It has the potential to be the largest demand for hydrogen in the state, even if it were 10% of demand, 10% of the vehicles, of light duty vehicles by, let's say, 2040, it would represent a very large set of demands for hydrogen that you could pretty much build a large scale hydrogen system around. And the state is very committed to building out refueling stations, at least over the next 3-4 years, to get us close to 200. We've got models available, commercial, they're great. And I realize that electric vehicles are, a lot of people don't call this hard to decarbonize sector, and electric vehicles are going to be, a critical part of this. But we only have a 15% market share right now of electric vehicles, and I think we have to be really careful not to sort of spike the ball on our own 15-yard line and decide, it's going to be 100% electric vehicles. We need to have, a portfolio here, and I think we may find that it's very important to have a lot of fuel cell vehicles in the mix over the next 10, 20, 30 years.
Great points. Thanks, Lou. Our final panelist is Dr. Joshua White, Deputy Division Leader for Science and Technology, Atmospheric, Earth and Energy Division at Lawrence Livermore National Lab. Josh?
Good morning, everyone. Thank you so much for inviting me. It's really great to be here with so many distinguished colleagues. So I'm Josh White. I'm a research scientist. My technical background is in civil and environmental engineering, but for the past 15 years, I've really been thinking about how we can use the subsurface, the Earth itself, for helping us meet our carbon neutrality goals. So looking at technologies like geologic carbon storage, geothermal energy, and now more recently, underground hydrogen storage. And so the hydrogen has lots of uses, really great uses that have been mentioned by the colleagues here. Another challenge that it could really help with is energy storage. As Naomi mentioned, if we have an electric grid that relies heavily on wind and solar and other technologies like that, we may have quite a bit of intermittency. When the wind doesn't blow and the sun doesn't shine, we will have fluctuations in our power supply. And so we're quickly moving from an energy generation challenge to an energy storage challenge. How do we actually store challenge so we can kind of flatten out those fluctuations? And there are a variety of solutions to this, but hydrogen is actually a very interesting one. It provides long-term stable energy storage, and potentially we could do it at very large scale. Currently, for example, we do this with natural gas. We store trillions of cubic feet of natural gas in the subsurface as an energy storage medium. And the big question is, could we do the same with hydrogen? And so that may actually provide a nice option for grid scale energy storage. It certainly wouldn't be the only solution. Pumped hydro, other batteries, lots of other storage techniques will continue, will play a big role, but hydrogen is definitely an interesting one to explore.
Thanks, Josh. Well, we've heard from each of our panelists one application. I think it's important to note that hydrogen is really has ubiquitous use across many sectors, and there are other applications as well, including things like the use in ports for maritime, shipping, aviation, potentially, as ammonia. We've seen hydrogen have lots and lots of different applications. So all of those are on the table for discussion today. I invite all of you watching to use the Q&A feature to submit your questions to our panel. Please include your name and affiliation. And to get us started with our Q&A, it's my pleasure to invite back Katerina Robinson to ask the first question on behalf of Senator Nancy Skinner. Katerina.
Hello again, thank you. So I'll just go ahead and ask a question that we hear a lot in the legislature. And I'm sure there'll be many other good questions today. My question is, so hydrogen can produce a lot of benefits on the electrical system. It can give us some of that seasonal storage, right, that we're looking for all the time of, how do we make sure that the solar and wind resources we have can be used off season, or even, more daily type of storage, moving some of that production to the times of peak demand when maybe we don't have the solar resources we need. But when we talk about hydrogen for the use of electricity, we always get questions about combustion, and does combustion of hydrogen actually produce an air quality benefit to a community where that combustion is occurring over a combustion of a natural gas. So if you're using natural gas to produce electricity in a power plant, is that going to be dirtier still than producing electricity with hydrogen? Or do you get air quality improvements using hydrogen? And could you get to zero air quality emissions using hydrogen? So I'm not sure who would like to answer that, but I'll start with that question.
That's a great question. Arun, you've been focused on life cycle emissions. Would you like to have first crack at that?
Sure. So it is a very important question that comes up often. I think we all agree that the long-term goal is to move away from combustion and move towards fuel cells, where we don't have this criteria pollutant or toxic emission issues. But while we are working to achieve that goal, is it worthwhile to think about hydrogen combustion in existing facilities? I think hydrogen does have a higher NOx challenge, and it's something that hasn't really clearly been drawn out or understood by the research community. I don't think there's consensus on what the increase in the NOx emissions will be. But if we think about all the natural gas power plants in the country, in California and the country, and how long it'll take to transition them away from fossil natural gas, being able to blend some hydrogen with that natural gas and use that hydrogen to generate power is attractive, because we're significantly going to be reducing the carbon intensity of the electricity that's being generated. And there are ways to control the NOx emissions from these power plants. So my, kind of a high level answer would be, it's one of those yes, but questions. So yes, there is a NOx issue, but I think if we look at it from a broader perspective, it is an option that's worth pursuing, and ultimately that can be resolved using technology.
Would any of the other panelists like to weigh in on this?
I might just jump in with a brief comment. So if you look at the overall NOx emissions, more than half of it comes from the transportation sector. And so to the extent that hydrogen offsets diesel and these types of things, we definitely will see a net reduction maybe in overall NOx emissions. But yeah, then when we get to combustion at point source power plants, we would really need to make sure they're designed to minimize NOx emissions, have scrubbers and so forth to make sure that they meet EPA attainment goals and so forth. So critical question, but overall it could have a very positive benefit for communities that are seeing high NOx emissions.
And I'll just add that anytime we replace combustion with a fuel cell, we're eliminating all emissions, right? So that's true for all the vehicles as long as they're fuel cell vehicles, but also a lot of end use. There's a lot of end use potential for using fuel cells to provide heat and power. And so there's zero combustion there either, and you can provide power for large facilities that way.
Yeah, maybe I just wanted to add that there are certainly some applications for which the research community still needs to clarify when and where NOx increase compared to combustion of pure natural gas. At UCI, we have done tests on stovetop burners and boilers that don't see necessarily in all cases an increase of NOx when you switch or when you blend hydrogen with natural gas. So there is definitely room for sort of improvement of burners, and especially for a certain percentage of blending of hydrogen to natural gas. There is not this problem has been shown that you don't see an increase in NOx. Only when you have very, very high hydrogen concentrations, that's when the flame temperature becomes higher than natural gas. Yeah.
Great, thank you for that. Well, moving on to our next question. It's from Barry Moline, who is at the California Municipal Utilities Association. And what's the difference between green, blue, and brown hydrogen and its availability? So I'm going to ask Josh to weigh in on this one.
Okay, I'd be happy to. I will first of all say the colors of hydrogen get very confusing. So this is the colors are a shorthand way of kind of describing how the hydrogen is produced. The hydrogen itself is not green. At the end of the day, we end up with the same molecule. So green hydrogen is, let's say, the long-term goal, where we would take renewably generated electricity. So think excess solar capacity, excess wind energy, use electrolysis, for example, to split water into hydrogen and oxygen. So there are no CO2 emissions. We end up with hydrogen, which is sort of an intrinsically clean product. And so this is really great. And so this is sort of the long-term goal. The challenge right now is green hydrogen is more expensive to produce than other sources of hydrogen. The prices are falling rapidly, and so pretty soon that may no longer be the case. But for the moment, green hydrogen is expensive. Currently, the vast majority of hydrogen on the commercial markets is produced from fossil fuel sources. And so here we get into gray and brown and black colors of hydrogen. And so the most common way is gray hydrogen, where we take methane, so natural gas, do something called steam methane reforming. So we basically mix water and hydrogen at high temperatures, water and methane at high temperatures to eventually produce hydrogen and downstream CO2. And so this CO2 then gets emitted to the atmosphere. And so this is really problematic because we end up with a green product, hydrogen. But if you look at the life cycle, we've actually put quite a bit of CO2 in the atmosphere. And so it really does not advance our climate goals. But then this opens up sort of interesting other colors of hydrogen. So there's one called blue hydrogen, where the idea is we do this steam methane reforming process, but we have CO2 coming off the back end, and it's relatively easy to capture that CO2 and, for example, inject it underground into a storage reservoir permanently. We basically dispose of it as we dispose of wastewater and other fluids we want to get rid of. And so if you look at this now, we have more or less a sort of a low carbon or almost carbon neutral way of producing hydrogen, even though it's coming from a fossil fuel source. And so this currently is cheaper than green hydrogen. So you're seeing a lot of market interest in it. From my perspective, and then I will mention, if you read the press, there are a million colors. You'll then see, pink hydrogen, which is produced from nuclear energy, white hydrogen, yellow, turquoise. It gets a little comical. And from a scientific point of view, I would just emphasize it's not really particularly useful to focus too much on the colors. we need to think about the fundamental goal, which is not putting CO2 in the atmosphere. And so in that sense, it's really better to think about different technologies in terms of their carbon intensity. How much CO2 or CO2 equivalents does this technology actually put into the atmosphere? I think that's a much more fair and meaningful way to compare different hydrogen generation technologies.
That's a great point, Josh. You know, I think we're spending a lot of time sort of trying to come up with definitions for these colors. And the truth is that there's so many nuances within each color now that if we focus on carbon intensity, we're more likely to keep our eye on the ball. Any other comments on the colors from our panelists? I think you did a great job summarizing that, Josh.
Naomi, I just want to add that, you know, green hydrogen is typically perceived to be from electrolysis, but we should consider hydrogen from other renewable resources like biomass, waste biomass, or municipal solid waste to be green as well, and they will have pretty low carbon intensities also.
Yeah, again, I think there's so many pathways within each of these colors. That's exactly right, Arun. Thank you for pointing that out. Our next question is from Sandra Faber at UC Santa Cruz. And her question is, what are the net requirements of the whole cycle if the hydrogen is made by splitting water? And is this practical? So Luca, you know, you've kind of got this background in electrochemical systems, so I'm going to give you first shot at this one.
Yes, thank you. Thanks for the question. The requirements for producing hydrogen through electrolysis are availability of a cheap renewable source, electric source, and the fact that it has to be cheap is really important to create cheap hydrogen. The electric input is the sort of biggest cost in when you produce electrolytic hydrogen. So having
we seem to be having technical difficulties. Luca, are you with us?
Yeah, I can hear you.
Perfect. We lost you for a second there.
Okay. Yes. So the electric cost of the that goes into the electrolysis is one of the biggest for electrolysis. So reducing the cost of the renewable source is very important. So we need to have the installation of water electrolysis or steam electrolysis close, preferably close to the renewable source. So when you have high solar radiation areas or high wind areas. Another requirement that we should consider, especially being in California, is the water availability. So we've done some studies trying to understand how much water we would need to produce the amount of hydrogen needed to decarbonize, for example, the ports of Los Angeles and Long Beach. And how much water we would need is not a negligible amount, but it's certainly a fraction of, for example, the LA aqueduct capacity. So we certainly need additional water compared to the one that we currently use today, and infrastructure to take that water to the place where we will produce hydrogen. And again, we might have sort of an infrastructure question of where is water most available, which in our state is more in Northern California, and where are solar and wind resources most available, which are predominantly in Southern California or, for example, offshore. So we certainly have that aspect to be considered. And also, just another point on water is the most available electrolysis technologies use pure water that needs to be purified, deionized. So another aspect that we should research on and develop is how can we produce hydrogen with, for example, low quality water, wastewater, or even seawater. In that case, this problem can be solved or addressed more broadly in the whole state.
Wonderful, thank you. Any other comments? Okay, moving on. Our next question from Bart Crows at the California Energy Commission is, could you speak about hydrogen leakage monitoring and its global warming potential? I'm gonna open this up and see who wants to chime in first.
So maybe I can provide some comments and the other panelists can add, Naomi. So hydrogen leakage is becoming a more and more serious concern as we think about different ways to deploy or transport hydrogen. And especially when we think about potentially injecting hydrogen into the natural gas infrastructure so that we can transition our natural gas pipeline infrastructure away from the fossil methane and towards renewable hydrogen. So we've been doing a lot of work on this at UCR, and definitely hydrogen being a smaller molecule tends to leak more. It doesn't necessarily leak preferentially, meaning if you have a methane hydrogen blend, hydrogen doesn't leak by itself, but the higher the hydrogen percentage, the more volume of the leakage that you're going to have. And it's an issue that's relatively straightforward if the leak is through cracks or other openings or damage or failure of the pipelines. And I think there's a lot of work that needs to be done on odorants that can be added and updating our safety and maintenance processes and all of those other things. But hydrogen also has a potentially embrittlement effect on materials. That's something that we're working towards resolving. So the short answer would be hydrogen leakage is an issue, but as we're already working towards addressing methane leakage from a climate perspective, I think hydrogen leakage can also be managed. Regarding the global warming potential, I think this is also a topic that's become of higher interest recently because we want to use a lot of hydrogen. And there's some debate about the actual effect of hydrogen and whether it's a short-lived climate pollutant. But I would say that if we manage to replace a considerable portion of our fossil resources with renewable hydrogen, the net effect would be a significant benefit in reducing greenhouse gas emissions.
Any other comments?
Yeah, maybe I wanted to add one comment. On the hydrogen leakage, we've actually done tests in our buildings at UC Irvine, trying to blend hydrogen with our natural gas infrastructure at low pressure. And we've actually seen that if there is a leakage, certainly hydrogen will leak, but it doesn't seem to be leaking faster than methane, at least from a low pressure natural gas infrastructure. So on a building, let's say grid, our experimental measurements showed the same rate of leakage between hydrogen and methane. On the global warming, there is a lot of debate, as Arun said correctly, and I think researchers are still trying to understand. There has been maybe a couple of reports coming out in the past few months that are only based on sort of modeling studies, and what they seem to say that the increasing hydrogen concentration can increase the lifetime of some global warming species like methane and water. But again, if we are already working towards a reduction of these methane uses and methane leakage on the ground, that will certainly be we will see certainly a net reduction of methane in the atmosphere, and therefore a sort of net positive effect on global warming.
I think just to add, at Stanford, we've been doing a lot of work on mitigating methane emissions. And what's really helpful is that we're just starting to develop a hydrogen economy. And we're going into it from the very beginning with this in mind and with tools in our toolbox from the historical studies on methane emissions that will enable us to optimize the systems. So with methane emissions, we know that the largest emissions account for the majority of volumes. and we are starting to understand which pieces of equipment leak in the largest volumes. And so we will be able to design our hydrogen infrastructure with a lot of these lessons learned in mind to ensure that those parts of the system that are analogous to the natural gas system are foolproofed and leak-proofed. Okay, moving on. The next question, also from Bart Crows, is there a potential for green hydrogen and ammonia production in California? I'm going to open this one up as well. Who wants to chime in first?
I'm not an expert, but definitely, I think the answer is yes. However, we have to manage to produce that green hydrogen because if we think about how much fertilizer we make and how much ammonia is needed, that would be quite a bit of green hydrogen. And that's where the emphasis should be, I think, at least for now. But it's definitely an opportunity to have significant effects on significantly reducing greenhouse gas emissions.
I'll chime in on that one.
Sure.
Certainly, building a large ammonia plant in California means you've got to know where your hydrogen's coming from. But that's true in general, right? As we build out this system, what we're trying for here is a large-scale system where we match demands and demand growth with supply and hopefully low carbon supply, green hydrogen, and getting that scale is what it's all about, and helping to bring the cost down through that scale. And ammonia is interesting, and I'm not an expert at all either, but California, I believe, uses the most fertilizer of any state in the country. I saw that somewhere, and I think we import all of our ammonia to produce fertilizer, and it just seems like if ever there was a place that should have its own ammonia production, it's California. So it does seem like a tremendous opportunity.
Absolutely.
Yeah, I just wanted to mention another application for ammonia. Certainly, I second what Lou said, that there are opportunities for ammonia production with renewable or low carbon hydrogen in California for fertilizers production, but also for the maritime sector. As a different, let's say, more handy energy vector to be used to decarbonize shipping. So, for example, we've done work at UCI trying to see how we could redesign powertrain for ships that could be transitioned from diesel, as they currently use, to ammonia fuel cells on the ship. We're also working on ammonia synthesis using electrochemical pathways. So instead of going through sort of the conventional sort of large-scale industrial Fischer-Tropsch process, Haber-Bosch process for ammonia synthesis, we're doing electrochemical synthesis that can be sort of done at a modular level at a smaller scale. So.
And I think just to add to that, I think there's also an opportunity here for the US to be an exporter of ammonia in particular to other countries that don't have necessarily the resources to produce their own hydrogen and ammonia in-house. So transporting hydrogen over very long distances would be enabled through ammonia production. Our next question is from Jim Hawley at Berkeley National Lab. And Jim says, the cost of green hydrogen is expensive. It's about $5 per kilogram. The Department of Energy's goal is to get this down to $1 per kilogram in the next decade. This is kind of referred to as the 111 goal. Broader deployment can reduce costs, but that's not sufficient to achieve the $1 goal. Can you describe the research your institutions are doing to help achieve this goal? So Josh, you're also at a national lab, and I'm sure have a lot of insight into this. I'd love to hear what you're doing at Lawrence Livermore.
Sure, I'd be happy to answer. We certainly are working on the hydrogen shot, this idea of can we really get down to $1? It's not my specific area of expertise. Maybe I will start with when we were discussing colors, green hydrogen, blue hydrogen. Why is blue hydrogen even in the mix? Why are we even thinking about it? And I think it's important to realize that currently we have a relatively a growing supply of green energy on the grid, but it's relatively small and it's relatively expensive to produce hydrogen. And so as a result, if we link the growth of the hydrogen economy and the hydrogen infrastructure to green hydrogen, then we're going to be very sensitive to the price of green hydrogen. You know, infrastructure is not going to grow when green hydrogen is very expensive, and only until we reach, you know, $1 or some crossover threshold will we see a rapid growth in hydrogen. And so this is really the reason why blue hydrogen is even being discussed. It sort of uncouples the build out of a hydrogen economy with the actual source of the hydrogen. So we can build pipelines, storage infrastructure, and then when we achieve this ambitious shot and green hydrogen becomes very cheap, we can actually immediately transition the source. And so it works very nicely. But to be honest, in terms of the actual generation technologies, it's really not my area of expertise, and I would defer to some of the other colleagues on the panel.
I can mention that in our study that I mentioned earlier, where we're looking at how to, create a hopefully fairly optimized hydrogen system for California, looking out to 2050. Over time, as the hydrogen demand grows, we're going more and more to wind and solar derived hydrogen, and we do find that if we use the entire Western interconnect of the United States, the whole Western set of states, to provide that hydrogen, you have many more opportunities for very low cost hydrogen and hydrogen that can be produced in off hours and that kind of thing. So I think it depends on our scenario, but about half of our hydrogen in the out years is produced in California, but about half of it's produced in places like Nevada and Utah and Arizona and other states. So I think we have, and then you could truck it in because you can actually truck hydrogen a long distance, but eventually you make pipelines. And if you have a large, highly utilized pipeline, that cost is also pretty cheap. You can move hydrogen a long distance that way. So I think we have to be open-minded about where the hydrogen comes from if we want to get large volumes cheaply.
I can add a little bit on the research going on at UCR. I mean, definitely I won't be able to speak for all the different faculty and researchers here. So some of the projects that I've been involved, and my focus is primarily on the development and deployment side rather than a fundamental material side. We've been looking at especially how to tie hydrogen into the electric grid, because we talked about long-term energy storage in the beginning. And to do that, we have to connect hydrogen to the electric grid, and also how to produce and supply hydrogen as refueling for the heavy-duty transportation sector. So Luca mentioned that the cost of electricity is one of the major costs in renewable hydrogen. And so would it be, it would actually make sense to co-locate the hydrogen production facility with the wind or solar farm, so that we can take advantage of the energy that's going to be not supplied to the grid, right? So we're actually, wasting a lot of energy by not putting it to use. So we're looking at ways to where to locate and from what resources these hydrogen production facilities, and how to supply them or connect them to the end user. So, trucking is a viable option for short distances, but it's not a good choice for long distances. So how to locate them where it makes sense. And also for off-road vehicles and equipment that use hydrogen, we're looking at that.
Maybe I'll just, I'll just briefly mention a couple of projects that we're doing specifically for electrolysis for production of hydrogen from renewable sources. One aspect is materials. So developing new electrocatalysts that are not noble or rare on Earth, that have a more robust supply chain, for example, of which we have more of them on Earth. So currently we have to use iridium and platinum. Other materials that can be substitute or partially substitute these materials as catalyst can be a good sort of an important cost reduction for electrolysis. And another point is lifetime. We need to find ways to increase lifetime of electrolyzers. So understanding degradation methods of these cells, especially when we couple them with renewable sources that are very intermittent and fluctuating. That's another aspect that must be looked at.
Yeah, and of course, when you say degradation, you're referring to the fact that as we run these electrolyzers, if we have intermittent power, the materials actually degrade over time and the efficiency goes down.
Right, yeah, thank you, yes.
So I'm going to take just a couple of seconds to plug the hydrogen initiative at Stanford, because we've got a lot going on in this space too, just for information for our viewers. When we think about reaching the 111 goal, I think 4 things really come to mind. The first is we need to bring down the renewable power cost. And that's a huge fraction of the current cost, right? We're currently up at $5. Actually, sometimes in cases higher than that per kilogram for renewable generated hydrogen. So we're looking at markets. I think there's some really interesting things happening right now around the cost of natural gas and how that's going to impact investment in the renewable sector that will hopefully bring down the cost of the renewable electricity. We're pretty excited about that. As Luca mentioned, we think that there's a big focus to be had on the electrolyzer side. So getting away from the expensive and potentially non-sustainable precious metals that are in electrolyzers, and finding innovative solutions to use the intermittent energy from the grid. And also using cheaper materials, right? We want to move away from expensive stainless steel to really cheap run-of-the-mill steel for some of these applications. A lot of the balance of plant costs that go into the cost of hydrogen per kilogram is around the construction of the overall facility. And the last thing I'll mention is market demand. So we're doing research around how markets will evolve and how we can enable those markets to evolve by participating in some of the hydrogen hubs that have been the DOE's announced funding for. There's $8 billion on the table to fund hydrogen hubs around the country. And California has made an announcement that they're going to establish 2 hubs, one of which has sort of been underway for a while in the Port of LA and one in Northern California. So research institutes are partnering with industry to really make this a reality. Okay, moving on. Our next question is from Daniel Shore, Congressman Scott Peters' office. You've mentioned that energy storage is a promising field for hydrogen. Since the round-trip efficiency of regenerative hydrogen fuel cells is much lower than the round-trip efficiency of battery storage technologies, and since long-duration battery technologies like iron, air, and liquid metal batteries are coming to market, what makes hydrogen more attractive? Josh, I think you were the one who mentioned long-duration storage at the beginning of this panel, so over to you.
Sure. Yeah, so I will say that the long-duration storage topic is a hot one. There is a lot of work and interesting new technologies. The beauty of hydrogen, I think, is just its simplicity. It looks very much like something we do today, which is natural gas storage. We store exajoules of energy in the subsurface for months at a time using natural gas, and doing the exact same process at an industrial scale is very easy to imagine. Whereas some of these long duration battery ideas, iron and so forth, they're interesting, but they are pre-commercial, they're in development right now. And the other thing is the surface footprint that we're talking about would actually be quite small, again, because we're using the earth itself as a huge natural container. We don't actually have to build out a huge infrastructure of surface batteries taking up quite a bit of space. So I would say that's the key interest in hydrogen. But I don't want to pit that against any other storage technology. The thing I would always emphasize is the magnitude of the challenge that we're looking at is huge. We emit so much CO2 into the atmosphere. We use an incomprehensible amount of energy every day. The solution to this is going to be a patchwork of technologies, and all of them deserve their day in the sun, so to speak.
Absolutely. Other comments?
Just to add to that, a couple of points. One is, there are applications where we are going to need a fuel, not electricity, and we talked about many of them in this panel. And so it'll be good to have hydrogen as that fuel, as it helps us with both criteria pollutant emissions and also the greenhouse gas emissions. But I think what makes hydrogen particularly attractive, for me at least, is that if we look at the energy infrastructure right now, we have three major components: the oil infrastructure, natural gas, and then electric grid. And if we lean heavily towards electrification and manage to get rid of, or at least minimize the use of oil and gas infrastructure, then we're going to have a lot of challenges related to resiliency and the robustness and problems like, for example, wildfires or other natural disasters occurring. So it's always good to have that infrastructure that uses hydrogen as its backbone, where it can complement the electric grid. And this way we'll not only have long-term storage, but also have much higher resiliency and reliability from our energy infrastructure.
I think that's a really critical point, right? Because here in California, when we have wildfires, the solar output in particular is vastly diminished because of the particles in the air and so on and so forth. And actually the power demand goes up because people are trying to air condition their homes, right? So we're trying to think about how we can add resiliency, which to date has really been provided by the natural gas system. So yeah. I absolutely agree with you. I think bulk chemical storage of molecules, in addition to the electrons that we have in the grid, is going to be really important. We are approaching our time commitment here. So I've got one last question to each of you. If you could make one change today to help support the growth of green hydrogen in California, what would it be? Lou, you're up.
Yeah, and I'm caught off guard. I don't know why I am. I'm sure I was supposed to know about this question. I think it's about getting that early investment, and I think the hydrogen hub opportunity is tremendously important to start to build systems here. And I mean, we have Southern California's got some stuff going. Northern California has a lot of little pieces in play, and I think now we have an opportunity to really start coordinating and having, to some extent, we got to rely on industry to make the investments, but also to some extent, we got to coordinate this and figure out, what it's going to look like in 5 or 10 years, at least have a rough idea so that everyone has some confidence that they go in on the demand side, they go in on the supply side, there's going to be something there. And I think really there's never been a better moment to make that happen.
Absolutely. Arun.
Only one thing that's an extremely, I think, a challenging question, but I think I would like to think about this from the perspective of low-hanging fruit and also addressing our biggest or most urgent challenges. So I think on both sides, we do have the climate disaster that's looming, but also in the South Coast where we are, the air quality is a major problem. We have very high rates of asthma, premature deaths, and things like that. So what I would like to do, as we get loose wish of infrastructure and hydrogen production in place, to deploy as many medium and heavy duty vehicles on the road that use renewable hydrogen and fuel cells to address the tailpipe emission from these vehicles, but also reduce the greenhouse gases.
Very good. Luca.
Yeah, I think if I had one wish, one application would be try to convert the ports. If you convert the ports or try to electrify the ports, and then whatever you can't electrify, use hydrogen for it. If you build up the hydrogen infrastructure and hydrogen production capacity needed to decarbonize the ports, that will, I think, create sort of a supply chain, a market that will be able to convert freight, light-duty vehicles and locomotives and aviation and so on. But it's kind of, we need it. We need the sort of the market capability of sort of keeping up with that demand, because we're going to need a lot of hydrogen to do that.
Absolutely. And Josh, you get the final word.
I would just say that the generation challenge is very important, but we just can't forget that this is an interconnected system. And so we need to think about transportation challenges and storage challenges hand in hand. And I think we learn by doing. And so to the extent that we can have incentives for pilot projects, pilot demonstrations where we really learn how to do this and demonstrate it's a great idea, that will only push the ball further down the field towards our carbon neutrality goals. So.
Well said. Well, thank you to each of you for providing your expertise today. I've certainly learned a lot, and I hope our audience has too. And I will turn it back to you, Sarah.
Thank you, Naomi. And thank you to all of our experts for joining us today, for giving us some of your time. What an excellent conversation. And of course, thank you to our audience for being here with us today. If you'd like to watch this briefing again, or have a colleague who was interested but couldn't make it, it will be posted on our website, along with the one-pager that has the contact information of the experts you heard from today. So of course, feel free to reach out with additional questions. Look out for future information on CCST briefings and other events. Thank you, everyone, and have a wonderful day.